In this video, I'm going to go over question 8 from the November 2016 paper 1 for IB Math SL. So it's a vector question. We're given vector OA and OB, which are basically point A and point B, because O is just the origin. And we're asked to find vector AB. So in order to find AB, we're going to subtract B minus A, terminal point minus the initial point, treating B as a point and A as a point. And that would give us 4, 1, 3 if we're showing work for this, minus negative 1, 0, 4. And just be careful with signs because of subtracting negatives. Sometimes we mess up signs in that process. So 5, 1, negative 1. Then find the magnitude. This is the big square root formula where you're squaring each component of your vector. It's like the distance formula. Make sure that each of these comes out positive when you square them. So I like to put them in parentheses when I write it down. This ends up being the square root of 27. We just leave it like that. So basic vector knowledge there. And then they give us the point C, or they tell us there is a point C, but they don't give us the coordinates. They ask us to show that the coordinates. Point C would be negative 2, 1, 3, if the vector from A to C is negative 1, 1, negative 1. So it's helpful to think here that if you start from point A and you add the vector AC, you're starting from A and you're traveling to C, so you should end up at point C. So we know point A was given to us at the beginning of the question is negative 1, 0, 4. We're adding the vector to get from A to C, which is given, and then we should obtain point C as a result, because that's where we'd be on the coordinate plane if we started from A and traveled AC. So showing that simple addition is a quick, elegant way of proving that that's the coordinate of C. Then the question switches gears and gives us a triangle, and the A, B, and C are the same A, B, and C, but we don't really need that information right at the beginning here. We have a triangle. It's asking us to write down an expression in terms of theta for the angle ADB. That's this angle here. So all that's testing is whether you know that because they're sitting right next to each other, they're a linear pair, that would be 180 minus theta. I'm going to label that in the picture. Might be helpful for us to see it later. Then write down an expression for the area of triangle ABD. Still in terms of theta. We're not trying to find any actual lengths, find any actual area here. I can use variables in this expression. So if I'm thinking about the formula that I know for the area of a triangle that we use all the time, 1/2 AB sine C. It's an equal sign. Does not look like one. Area equals, we can use any two sides of the triangle and the included angle. Since we want this thing to be in terms of theta, we're going to use this angle, which means the sides would be BD and AD. So we can say area equals 1/2 BD as one of the sides, AD, and then sine of 180 minus theta. And that's sufficient for this question. That's really all it's asking, is that we know how to fill in an area formula using the pieces of this triangle. And we're going to need it in the next part of the question. So each of those was only worth 1 point. But now we're given this ratio. The area of the triangle on the left over the area of the triangle on the right is equal to 3. Show that BD over BC equals 3/4. This is all ratios. We don't actually care about the areas. We should not be trying to calculate them using our vector information from the beginning of the question. It's just too complicated, and it's not necessary. So watch as we set up a ratio of these areas just in general terms using the letters from the picture. So BDAD sine of 180 minus theta. This was the triangle we just wrote the area of, ABD. And then if we look back to the triangle, we need an expression for ACD, which was the triangle on the left. So let's click back to that. So there's ACD. So its area expression would be DC and AD and sine theta. So DC, AD, and sine theta. We'll put that on the bottom of our fraction. So 1/2. DC was one of them. AD was another one. And then sine theta. This is supposed to equal 3. And what we can see here, or what we're supposed to see, is that most of this is going to cancel out. 1/2 cancels out. AD cancels out. And even the sine of 180 minus theta and sine theta cancel out, which many students did not recognize. So if you had the coordinate plane, theta we were told it was acute, so it's going to be somewhere here in the first quadrant. 180 minus theta would mean that very same angle, but over here, right? Because this angle would be 180 minus theta. These two angles will have the same sign because they have the same opposite over hypotenuse. So that's just something we are expected to recognize, that an angle and its supplement have the same sign. Therefore, those are two equivalent things and they cancel out. So what we're left with is BD over DC equaling 3. you could think about that as 3 over 1, so that if you had the visual, I'll just draw that stretch from the picture so we don't have to keep clicking back to it. It was a B over here, it was a D in the middle, and it was a C over here. And I don't know the actual lengths, but I know the ratio is a 3 to 1 ratio. So you're thinking of BD as this length and DC as this length. They're in a 3 to 1 ratio, which means BD over BC, which was what this question was asking us to show, must be equal to 3 over the total distance, which would be 4. And even just this picture is evidence enough of that. If you're thinking about BC as 3 plus 1, right, the distance from B all the way to C. So that's how we're supposed to show that without actually calculating any of these lengths or areas. And then we have to bring our vectors back into play for part E. There's a few ways we could go about doing part E. So hence or otherwise find the coordinates of point D. So it's nice that we have this picture here. I'm gonna redraw it, and I'm gonna label B and C with the coordinates that we were given earlier in this question. So this is B, D, and C. C was -2, 1, 3. B was, I've already forgotten it, let me look it up here. It was 4, 1, 3. We can see that they have the same Y component and the same Z component. Give myself a little more room to work this out. It might be helpful for you to think about, if we're trying to find the coordinates of this point D, the vector to get from B to C would be a -6 for your horizontal component. You can get this by subtracting, right? C minus B. -6, 0, and 0. And instead of trying to travel starting from B, instead of trying to travel that entire vector, we want to travel only this far. So it's going to be a vector that goes the same direction as -6, 0, 0, but has a shorter magnitude. So one approach we could do is to scale this thing all the way back to the size of 1 and then scale it up. So that would be called getting a unit vector. So that's one option. Or we can just think about the ratio that we know. So if the ratio of BD to BC is 3 over 4, right, that's what we just proved in the previous question, then we just want to take this vector, -6, 0, 0, and multiply it by 3/4. And then add it to the point B. So let's see how I can write that down in a way that would be clear. So we want to start from point B, and we want to add 3/4 of the vector -6, 0, 0. I think that makes sense. I'll replace point B here with the 4, 3, 1. See if this gets us the right answer, or the 4, 1, 3 rather. So here we have 4 plus 3/4 of -6. So we do have to do a little bit of math there without a calculator, which is a bit of a chore. It's going to give us -1/2. So that's -1/2. The other ones are quite a bit easier because it's 1 plus 3/4 times 0 and 3 plus 3/4 times 0. If you want to see the calculation there for the -1/2, it was 3/4 times -6. I did it mentally, but what I did was I reduced this to 3 over 2, and I ended up with 4 plus 9 over 2, and it would be negative, so 4 minus 9 over 2. And that's -1/2, so that's where that came from. And then these would be the coordinates of D. And that's it.